Hello everyone. Today I'm going to present you our project entitled Optimal Dumping with Hierarchical Adaptive Quadrature for Efficient Fourier Pricing of Multi-Asset Options in Lévy Models, which was done in collaboration with Dr. Christian Bayer, Dr. Shihab Ben Hamouda, Professor Antonis Papapantoleon, myself, Michael Samet, and Professor Raul Tempone. Efficient pricing of multi-asset options is a challenging problem in quantitative finance. Fourier-based pricing methods become very competitive to alternative techniques because the integrand in the frequency space, the Fourier space, has often higher regularity than in the physical space. However, when designing a numerical quadrature method for most of the existing Fourier pricing approaches, two fundamental aspects affecting the numerical complexity should be considered carefully. First, the choice of the dumping parameters that ensure the integrability and also control the regularity class of the integrand. Second, the effective treatment of the high dimensionality of the integration problem. To address these challenges, we propose in our work an efficient numerical method for pricing European multi-asset options based on two complementary ideas. First, we smooth the Fourier integrand via an optimized choice of the dumping parameters based on a proposed heuristic optimization rule. Second, we use the adaptive sparse-based quadrature, which is based on sparsification and dimension-adaptivity of the quadrature grid to accelerate the convergence of the numerical quadrature in high dimensions. Through an extensive numerical study on the basket and rainbow options under the multivariate geometric Brownian motion and some multivariate Lévy models, namely variance gamma and normal inverse Gaussian, we demonstrate the advantage of adaptivity and also our damping parameter rule on the numerical complexity of the quadrature methods. Moreover, we reveal that our approach achieves substantial computational gains compared to the Monte Carlo method for different dimensions and parameter constellations. We start by defining the problem setting and pricing framework. In this work, we consider the pricing of basket put and colon min multi-asset European style options, for which the respected scaled payoffs are given by the following formulas in equation 1. The Fourier transforms of these payoffs are respectively given by equation 2 and 3 and their corresponding domains definition. As for the asset dynamics, we consider three models: the multivariate geometric Brownian motion and two multivariate Lévy models, namely the variance gamma model and normal inverse Gaussian model. And in the table 1, we provide the discounted characteristic function for each of these pricing models, which are given by the following formulas. And based on the inverse generalized Fourier transform theorem and also Fubini's theorem, we can derive the multivariate Fourier valuation formula, which was derived initially in its univariate formula in the paper introduced by Lewis. And the value of the option price, which is given by V as a function of model parameters and the payoff parameters, is given by the following integral, where G represents our integrand, and which depends on a dumping parameter which needs to belong to the intersection of two sets, one delta P bar intersect delta X, which we will define in the following section. So we now move to the strip of regularity. To ensure the L1 integrability of the integrand G in the Fourier valuation formula, a vector of dumping parameters denoted by R, which belongs to RD, is introduced, and which has to belong to delta V, which is the intersection of delta P bar and delta X. Delta P bar is the strip of regularity of the conjugate of the payoff transform, which is provided for each of the payoffs in table 2. And delta X is the strip of analyticity of the characteristic functions, and which is provided for each of the characteristic functions in table 3. The damping parameters affect considerably the smoothness of the Fourier integrand and hence the error convergence behavior of the numerical quadrature. There is no precise analysis in the literature on the effect of the damping parameters on the convergence speed of the quadrature methods, nor there is any guidance on how to choose them to improve the numerical performance, especially in multivariate setting. Also, the effective treatment of the high dimensionality of the integration problem in the Fourier space, because using naive tensor product quadrature suffers from the course of dimensionality. To alleviate these challenges, we enlist our contributions of this work. So we propose an efficient numerical method for pricing European multi-asset options based on two complementary ideas, smoothing the Fourier integrand via an optimal choice of the damping parameters based on a proposed heuristic optimization rule, and by approximating the Fourier integral using adaptive sparse-based quadrature, hence accelerating the convergence of the numerical quadrature. We also revealed that our approach achieves substantial computational gains compared to the Monte Carlo method for different parameter sets and dimensions under the multivariate GBM, variance gamma, and normalized Gaussian. We now define the characterization of our optimal damping rule. So, motivated by quadrature error bounds, which are presented in paper provided in the reference, and also conducted numerical experiments, we propose a heuristic rule for choosing the damping parameters that improve the convergence of the numerical quadrature method, which consists of solving the following not smooth constraint optimization problem defined in equation 5, and which consists of minimizing the infimum norm of the integrand G when subject to error belonging to the strip of analyticity of the integrand. We now denote by R star the vector of these optimal damping parameters, and we also exploit the property that the integrand in equation 4 attains its maximum at the origin, U equal to 0 in RD, null vector. Thus, solving the problem in 5 is equivalent to actually solving a simpler optimization problem, which is given in equation 6 as minimizing the peak of the integrand at the origin. In figure 1, we provide on the left the shape of the integrand with respect to some values of the damping parameters, and on the right-hand side, we provide the error convergence of the relative quadrature error with respect to the number of quadrature points n when we use actual Gauss-Laguerre quadrature for the European put option under variance gamma with the following parameters. Now we move to the adaptive sparse quadrature section. The d-dimensional quadrature operator is given by a tensorization of univariate quadrature formula over Rd, where the quadrature operator is a function of the dimension and also an index set, and is defined as a sum of the multi-indices, a vector of integers belonging to the set of multi-indices, which defines what is the quadrature method of different mixed difference operators applied to the quadrature operator, which it's to the mixed difference operator, which itself is defined as a tensorization of the difference formulas on the multivariate quadrature formula, and the multivariate quadrature formula is defined as a tensorization of univariate quadrature rules, which are defined with respect to a function m, which is a level to nodes function mapping the number of quadrature points corresponding to a given level, and the univariate quadrature rule consists of simply taking a weighted average of the function evaluations, the function which is the integrand, at abscissas, which correspond to a set of the quadrature points, which are in fact roots of polynomials for Gaussian quadrature, and multiplied by weights which are also depending on the quadrature method that is used. So the choice of both the strategy of the construction of the index set I, calligraph I, and the hierarchy of quadrature points determined by the level to nodes function m define the hierarchical quadrature methods. For instance, tensor product, small x sparse grids, and adaptive sparse quadrature, for which the level to nodes function and the index set are all provided in table 4 for each of the methods. The construction of the index set of the adaptive sparse quadrature is performed adaptively and in a greedy fashion through profit thresholding. So new indices are selected iteratively based on the error versus cost profit rule with a hierarchical surplus, which is defined by p beta, p subscript beta, by the ratio of the absolute value of the error contribution divided by the work contribution, which are both defined below. Now we move to the numerical experiment section. For illustration, we only provide the numerical results for pricing European options for assets under variance gamma model. However, the results were consistent and can be found the same under other pricing models, namely geometric Brownian motion and normal inverse Gaussian, and different parameter sets and different dimensions. And for more reference, you can check the work that we've done, which is published on Archive. So in table 5, we provide the parameter sets for each of the pricing model for like 4 examples, the corresponding parameters, reference values with their corresponding statistical error with 95%, and also the vector of the optimal damping parameters that is obtained using the heuristic optimization rule that we had proposed. Figure 2 illustrates the effect of sparsification and dimension adaptivity. We observe the convergence of the relative quadrature error with respect to the number of quadrature points for all tensor product, small x sparse grids, and adaptive sparse grids quadrature for European 4 asset options under variance gamma model when the optimal damping parameters or R bar are used. On the left, we illustrate the example 2, and on the right, we illustrate the example 4 from table 5. We observe that the adaptive sparse grids quadrature has the best convergence behavior compared to the small x sparse grids and tensor product quadrature. As we can see, it uses around 1,000 points to reach tolerance level of 10-3, whereas the tensor product quadrature would need at least 4,000 quadrature points to reach the same level of accuracy. As for the effect of the optimal damping rule, we observe under the variance gamma model the convergence of the relative quadrature error with respect to the number of quadrature points n for the adaptive sparse grids quadrature method for various damping parameter values. And on the left, we provide the example 2, and on the right, we provide the example 4. You observe that for the vector of optimal damping parameters, which is illustrated by the red curve, we have the optimal convergence behavior. We have a better rate of convergence than in the other method, which also provides sort of erratic behavior for other damping parameters, which are in the neighborhood of the damping parameters, of the optimal damping parameters, which are obtained using our heuristic rule. As for, we provide in table 6 a computational comparison of quadrature methods with optimal damping and Monte Carlo method. We provide the errors, CPU times, and function evaluations comparing the Fourier approach combined with the optimal damping rule, the best quadrature method with the Gauss-Laguerre quadrature rule against the Monte Carlo method for the European basket and rainbow options under the multivariate variance gamma pricing dynamics for various dimension. And the reference values with their corresponding statistical errors are provided in the table. We observe, for instance, that to achieve the same level of accuracy for using adaptive sparse grids quadrature, we use only 4.7, around 5% of the work that is needed to achieve the same level of accuracy using the Monte Carlo method, which, for instance, in the example 1 requires 106 seconds, whereas the Fourier approach, which is combined with hierarchical adaptive sparse grids quadrature and optimal damping, requires only 5 seconds. And in the example under the colon min, which is example 3 and example 4, we can see that we can achieve the same level of accuracy using our Fourier approach method using only around 0.57% of the CPU time that would be required by the Monte Carlo method to achieve. Thank you for your attention.